Okay, so we'll talk about operators in infinite dimension. Let's go back to our example when we said that there's a proton in the center and there's an electron that is going around this proton in a sort of wave fashion. And when we said for this electron to have a closed orbit, this condition needs to be satisfied. Lambda is the wavelength of the wave, r is the radius of the circle. Now you see there's a constraint, and because of this constraint there is a quantization which has appeared, and also because of the wave nature, where n cannot assume all the values, it can only assume integer values for wave to match with itself where it started. This should hold true. So this is quantization which has appeared, but on top of that, if we just talk about this particular state, let's say we just fix one n, if you just, let's say if we talk about the variable theta, the variable theta is actually continuous in nature, and the position of this electron is not really discrete, is present over any point on the circle. So theta can be anything, and if it's really moving, then theta can be anything. If you start from 0, it can be anything. Okay, so how do we talk about the same construct here? So we can generalize it like this. Let's say this is our state. Then this can be written as, now I'm not really talking about on which psi and phi depend, I'm just telling a generic thing here. Psi and d, I don't know, dx0, dx1, whatever it depends on, these two variables depend on. Okay, also we can see that if there is an operator in the case of matrix, that discrete case, we were calculating this particular thing as row vector operator A. So it's following the same construct, but it does not have discrete nature, but is a continuous thing. And this can be written as phi star operator A psi dx0 dx1 and so on, whatever. And this, if you look closely, this is nothing but the expectation, I'm sorry, this is just definition. But if phi is same as psi, let's say phi is same as psi, which means we are talking about psi a psi. If you write it this, we get psi star a psi dx 0 and so on, and this is called the expectation value of operator A. For example, if you want to find the expectation value of theta, then what we'll do is simply phi theta is operating, and then we get theta psi dx 0 and so on. And we also have talked about Hamiltonian operator. We know that h psi equals E psi, where E is the energy of the system of this particular electron. Then if we write something like this, then this is psi h psi dx0 and so on, and this actually gives us the expectation value of the energy. Here it gives the expectation value of theta. So how the operator is acting? So this is basically a weighted sum. This is the same as here. This is actually weighted sum over discrete vector. This is a weighted sum over continuous vector. And we know whenever we have a weighted sum, that is nothing but the expected value of the outcome. So what do you mean by expectation values? That if you make many measurements of theta, what will happen is that um, uh, well, actually this is not expectation value of E, but E itself. There's nothing like expectation value of E. So it's the E, because we know that this satisfied. This is always satisfied. Okay, but here is the expectation value of theta. So how is this expectation value of theta? Because if you can actually write it like this, theta is not going to do anything to that, to this particular vector, and this can be rewritten as theta psi star psi dx0 and so on. We know that this is the probability density, and probability density multiplied by theta, that is what is the probability density of certain theta. This is a weighted sum here. So, and that gives us the expectation value of theta, which means that if you make many measurements, and you will find your electron at various thetas, and if you take an average of that, that is nothing but the expectation value. So this is the value which will be which measurement will which many measurements will confirm that many measurements will have an average value of this particular expectation. This is what we expect when we measure. Certainly every theta will be different, but this is a weighted sum, which means the aggregate of all the measurements will be this, and that's why these two angular things have been used here, because this is not really theta, it's the expectation value of theta. Now these are different from these because here it's not really state, it's not really a state thing, it's not really a state vector or anything. It's just these two angular brackets are telling that this is actually the expectation value of theta.